Welcome to this explainer. Today, we are going to completely unlock the secrets to mastering your computer science and information technology exams. Whether you are sitting for Cambridge syllabus codes 0417, 0478, 2210, 9618, or specifically the 9626 IT Section 13.1, we are treating your exam strategy exactly like a top-tier legal brief. Think about it for a second. A brilliant, highly paid lawyer doesn't just walk into a courtroom and start shouting random, disconnected facts at a judge. No way. They build an airtight case, they present concrete evidence, they structure an undeniable logical argument, and they lead the jury to an absolutely inevitable conclusion. That is exactly how you need to approach your Cambridge computer science exams from this moment forward. Right now, I want you to visualize a real past paper question. Imagine two typical students sitting down, feeling the pressure, staring at this exact paper. Let's call them Alex and Sam. Alex is a walking, talking encyclopedia. When confronted with a high-mark question on advanced technologies, Alex completely overloads the page with raw computer science facts. We are talking listing every single technical detail about egg sensors, LiDAR frequencies, and DNA sequencing. But Alex provides absolutely zero critical analysis. The examiner is literally sitting there with a red pen asking, "Okay, so what?" Then we have Sam. Sam feels the time ticking down, panics, rushes into the answer, and completely misses the command word requirements. Sam might actually write a brilliant, highly detailed explanation, but because the question explicitly asked to evaluate and Sam only described, all those high-tier marks are instantly lost. Today, in this explainer, we are going to ensure you absolutely do not make the mistakes of Alex or Sam. By the end of our time together, you will know exactly how to construct your answers with the surgical precision of a master strategist.
The stakes here are incredibly high. Look at this quote. When a senior examiner specifically takes the time to publish a report calling out a syllabus section as one of the most misunderstood areas in information technology, you need to pay very, very close attention. The examiner reports consistently show that candidates treat these advanced technologies, specifically the Internet of Things, molecular data storage, and autonomous transport, as completely isolated, separate topics. They study them in separate silos, they memorize flashcards for them independently, but the Cambridge syllabus, particularly when we get into those advanced assessment objectives that separate the top grades from the average grades, absolutely demands that you see the entire interconnected ecosystem. Why are they so misunderstood? It's simple, because students rely on basic, low-level definitions rather than analytical depth. They completely fail to recognize that the evolution and implementation of these specific technologies are deeply, fundamentally interconnected. You literally cannot scale one without the others. We are going to completely dismantle that misunderstanding right now, today, and rebuild your knowledge base exactly the way the marking schemes desperately require you to think.
Here is the exact docket for our legal brief today. 1. Core principles. 2. The procedural framework to approach complex questions. 3. Critical analysis skills. 4. Top examiner warnings. And 5. The golden rule.
Let's move into Section 1, Core Principles, setting the baseline. We have to begin with the theory, because understanding the precise technical architecture of these technologies is your very first crucial piece of evidence. You cannot build a compelling analytical argument on a shaky foundation. In the Cambridge marking scheme, this falls under Assessment Objective 1, Knowledge and Understanding. But as we know, knowing the basic definition is only your entry ticket. Understanding the theoretical architecture and the precise causal relationships is what actually gets you into the higher mark bands. We must clearly define these three distinct pillars, always keeping in mind that examiners award significantly higher marks to candidates who make cross-topic connections. Let's establish our baseline right now. First, the Internet of Things, or IoT. This represents the massive network of physical objects embedded with sensors, processing ability, software, and connectivity, allowing them to collect and exchange massive streams of real-time data over the Internet. Next, molecular data storage. This is the bleeding-edge concept of encoding massive amounts of binary digital data into the base pairs of synthetic DNA or other complex molecular structures. This offers unprecedented, almost unimaginable data density and longevity compared to traditional silicon. Finally, autonomous transport systems. These rely on artificial intelligence, complex LiDAR arrays, and real-time edge processing to navigate and operate vehicles safely without any human intervention whatsoever. Now here is exactly where Alex, our imaginary student from earlier, loses all those marks. Alex defines all three of these perfectly, flawlessly, but then Alex stops. To get the top-tier marks, you must integrate them. Consider this scenario.
An autonomous transport fleet operating globally relies on an immense decentralized network of IoT sensors embedded in roads, traffic lights, and other vehicles just to function safely. This massive continuous influx of IoT data from millions of autonomous vehicles creates a critical data storage crisis. Traditional silicon-based cloud servers simply cannot hold it all sustainably or economically. So what is the ultimate solution? Molecular data storage, which can archive these colossal petabyte-scale historical datasets for long-term algorithmic machine learning training. That, right there, is a cross-topic connection that makes examiners reach for their green pens to award top marks. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Moving on to Section 2, the procedural framework, step-by-step processing.
You can have all the computer science knowledge in the entire world, but if you do not format it according to the assessment objectives, your raw knowledge is totally useless. Let's move from the what to the how. This 5-step procedural framework is your ultimate blueprint. 1. Deconstruct the question. 2. Extract relevant data. 3. Execute your analysis with clear notation. 4. Verify. 5. Present using the correct terminology. Step 1 is absolutely the most critical part of this entire process. Deconstructing the question. You must decode the specific command words used in Cambridge exams. Are they asking you to describe, explain, analyze, or evaluate? Listen to me carefully. If the command word is evaluate and you only explain, you cap your marks instantly. You hit a ceiling that you cannot break through, no matter how much you write. Step 2 involves extracting the core data from the specific scenario provided. Step 3 is executing your analysis, and here I highly recommend using the PEEL framework. P-E-E-L. Point, evidence, explanation, link. Make your point about the technology. Provide evidence from the source material or scenario. Explain the technical mechanism in detail, and finally, link it back to the specific context of the question. I want to do a quick 30-second mental challenge with you right now. As I read out the next sections, I want you to try and spot exactly where I am making a point, providing evidence, explaining the tech, and linking it back. It's a game changer for your writing structure. Step 4 is verification. Did you actually answer what was asked? And Step 5 ensures you are using authentic, high-level computer science terminology, not generic layman's terms. Do not write, "The car uses cameras to see." No. Write, "The autonomous vehicle utilizes edge computing and computer vision algorithms to process real-time visual data." See the difference?
Section 3. Critical analysis. Building your case.
This is the domain where top-scoring candidates truly stand out. This is Assessment Objective 3. This is where we leave both Sam and Alex in the dust and where we secure those vital A and A-star grade boundaries. Critical analysis isn't about knowing more facts than everyone else. It's about doing significantly more with the exact same facts everyone else has. To argue your case effectively, you must demonstrate evaluative thinking by actively questioning assumptions and justifying every single decision with hard, interpreted evidence. Questioning underlying assumptions is a true hallmark of a top-tier exam paper. For example, a question might present a scenario where a smart city implements autonomous public transport to reduce traffic congestion. The underlying assumption hidden in that scenario is that the existing IoT infrastructure in that city is robust enough, with low enough latency and high enough bandwidth to actually support it without catastrophic network failure. A brilliant candidate will spot and explicitly point out that assumption. You must also consider different perspectives. What are the operational benefits for the logistics company versus the severe data privacy concerns for the ordinary citizens who are constantly tracked by these pervasive IoT networks? When you justify your decisions, rely on solid evidence extracted straight from the scenario. And finally, evaluate the limitations. If you propose molecular data storage as a massive archival solution for a company's data, you must acknowledge the major limitation. While the data density is genuinely incredible, the read and write latency is currently far too slow for any kind of real-time operational data access. That level of technical nuance is exactly what the examiner is searching for.
Let's look at exactly how this transformation happens. This perfectly illustrates the difference between a weak answer that merely lists features and a strong comparative analysis that actually evaluates. If a Cambridge question asks you to compare traditional cloud storage farms with molecular data storage for an autonomous vehicle logistics company, our friend Alex will just list features. Alex will write, "Cloud storage uses a lot of electricity. Molecular storage uses DNA. Cloud storage is really fast." That is disjointed. It's elementary. It doesn't analyze anything. A strong candidate uses comparative connectives. We are going to do a live rewrite right now in our heads. Think of a 60-second timer counting down. We are going to turn those red pen marks into green check marks. Here is the transformed, high-scoring version. Whereas traditional cloud storage provides the low-latency read and write access strictly required for real-time IoT navigation data, it is heavily constrained by an immense physical footprint and massive energy consumption. Conversely, molecular data storage offers unprecedented archival density for storing long-term machine learning data sets. However, its current read latency makes it entirely unsuitable for real-time autonomous processing. Do you hear the massive difference there? Words like whereas, conversely, however. These specific connectives physically force you to evaluate. They literally tie your arguments together into a cohesive professional legal brief that an examiner cannot help but give full marks to. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to Ace the Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, we are moving to Section 4, Top Examiner Warnings, Avoiding the Traps. What we are about to look at right now isn't guesswork. It isn't a theory. This is extracted directly, word for word, from the Cambridge Principal Examiner reports. These are the literal notes that the actual people marking your papers publish every single year, practically begging students to stop making the exact same predictable errors. We are going to do a highly interactive workshop segment right now. Imagine a 60-second timer flashing on your screen. First challenge, data scan. Look at these 3 mistakes. Mistake number 3, providing answers not specific to the given context. This happens all the time. If a complex scenario is specifically about a rural agricultural farm using IoT sensors to monitor soil moisture, and you write a brilliant, highly technical paragraph about how IoT sensors help manage traffic lights in a dense smart city, you will get 0 marks. Literally 0. Why? Because you completely miss the specific context of the source data. Mistake number 2, format and presentation. If the command word asks for a structured report format and you just write a sprawling essay, you instantly lose easy presentation marks. But mistake number 1 is without a doubt the most dangerous, confusing cause and effect when dealing with complex, multi-layered computer science technologies. Let's break that down immediately with our second challenge.
Challenge 2. Find the flaw. To avoid that first major trap, you must always cleanly separate the cause, which is the technology's initial trigger, from the effect it produces, ensuring you never flip them in your evaluation. I am going to show you a flawed sample paragraph, and I want you to spot the exact sentence losing marks. Here it is. The autonomous vehicle rerouted itself, which caused the IoT traffic sensor to detect a massive traffic jam. Did you spot the massive flaw there? The student completely reversed the logical flow. The autonomous transport system's physical rerouting is the outcome. It is the effect. The IoT traffic sensor out on the street detecting the congestion is the catalyst. It is the cause. In a highly stressful, high-pressure exam environment, it is terrifyingly easy to accidentally mix up the input and the output. When you are writing out your Peel paragraphs, you need to actively, mentally label your variables. The molecular storage archiving the data is the effect of the autonomous fleet generating way too much data. Keep your timeline perfectly linear and completely logical.
Here is a phenomenal strategy to keep all these moving components perfectly straight under immense exam pressure. Anchor your memory by creating a personal mnemonic from the key terms. We are talking about IoT, molecular data storage, and autonomous transport. IMA, or maybe you prefer MIA, molecular IoT autonomous. Whatever actually sticks in your brain. Let's jump into challenge 3, speed writing. You have exactly 30 seconds on an imaginary on-screen clock counting down right now. Your task is to mentally draft one perfect Peel paragraph linking these 3 technologies. Ready? Go. Point: autonomous transport scale-up fundamentally relies on both IoT networks and molecular storage. Evidence: autonomous vehicles use dense arrays of IoT LiDAR sensors. Explanation: these continuous sensor streams generate petabytes of unstructured data daily, far exceeding local silicon storage capabilities, thereby strictly requiring off-site, high-density molecular archiving. Link: therefore, the long-term viability of global autonomous logistics is directly and intrinsically dependent on commercial advancements in molecular data density. Stop the clock. That took less than 30 seconds to conceptualize, and I promise you, that is a top-band grade-saving answer.
Section 5. The Golden Rule. Securing the method mark.
We have covered the core principles, the step-by-step procedural framework, the Peel format, evaluative critical analysis, and the examiner traps to avoid. We've built the complete computer science answering system. But what happens if you just freeze? What happens if you are calculating complex data transfer rates for a massive IoT network and you mess up the math under pressure? That brings us to our final system and our 3 rules that guarantee top marks. Rule 1, command word decoding. Rule 2, Peel framework application. And Rule 3,
The time management matrix, which absolutely includes this golden rule. Never just jump to the final answer. Systematically show you're working, because those method marks are awarded for the process and can literally save your grade even if your final conclusion is totally incorrect. This is an explicit examiner alert. In computer science and IT, pure logic is highly valued over just getting a lucky final number. If a question asks you to calculate the required storage capacity for a fleet of autonomous vehicles over a year, and you perfectly lay out the entire formula, multiplying the data per second by the number of sensors, by the time in seconds, by the vehicles, but you accidentally drop a zero in your very final calculation, showing you're working secures the vast majority of the points anyway. These are called method marks. They are the examiner's built-in fail-safe, rewarding you for having the correct systematic procedural processing, even if the final execution had a minor human error. Never, ever write down just a final number. Treat it exactly like a high-level math exam. Clearly prove your structured thought process on the page. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGSC to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGSC and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.
I am going to leave you with this final, provocative question. To truly test your new evaluative thinking skills, how would you draw cross-topic connections between all 3 of these advanced technologies to solve a massive real-world problem? Think about global supply chain crises, or maybe climate change logistics. How does the data flow from the physical world via IoT navigate dynamically through the physical world via autonomous transport and ultimately get preserved for future generations via molecular storage? Think about it, build your case, and I will see you next time.